In a previous tutorial, we ran a SZMAP stabilization calculation on cyclone dehydrator system, or 4STD. In this tutorial, we will analyze the results in VIDA. We will use the watercolor VIDA extension to set the grid styles for viewing. And we will also use the water orientation VIDA extension to show the binding pocket water orientational preferences. Here's the workflow that will follow. First, we'll open the results in VIDA. Next, we'll run the watercolor extension and then analyze the grids in the order. Airport grid, this compares the ligand with water. The complex grid, this provides information about the role of water in the complex. The stabilization grid, this helps answer the question, does water hurt or help binding? The grid types that we are going to look at are listed here. The neutral difference-free grid maps the polarity throughout the binding site. Stabilization grids describe the binding reaction, that is, the complex minus apo minus ligand. Stabilization grids have negative energies, where water enhances binding affinity, and positive energies, where it decreases binding affinity. Van der Waals grids, these show a component of the energy that is not part of the difference-free energy. Order grids, these show the fraction of water entropy lost due to the electrostatic interactions. And finally, mask grids, these are an accurate description of the solvent accessible surface, calculated as regions where the minimum Coulombic interaction plus Van der Waals energy is below a certain threshold. Let us now take a look at the SZMAP stabilization results in VIDA. First, load the results. Click on the arrow to see the full contents of any item in the list window. Next, run the SZMAP watercolor extension. What does the watercolor extension do? It sets contour levels to better starting values and also changes the colors and the rendering styles so that the various grids are easily distinguishable. It also hides all protein atoms that are not near the binding site. At this point, it is desirable to zoom in or increase the scale of the objects in the 3D window. Next, let us take a look at the grids that I talked about earlier on. We are going to use League Disp APO as an example. Click on the neutral diff APO free energy grid. The neutral difference grids represent the difference between standard water and uncharged water. An uncharged water molecule is a proxy for hydrophobic atoms in the ligand. The watercolor extension configures them as a pair of contours. Negative in gold or yellow represent areas where standard water has low values. For delta G and delta H, standard water is more favorable here. And positive areas are in purple. These represent areas where uncharged water has lower values. The hydrophobic or hydrophilic pattern within a site is matched by high affinity ligands. If you select the Van der Waals grid, This shows a component of the energy that is not a part of the difference-free energy. Van der Waals grids are always shown in green contours, and they're about -2 kilocalories per mole, and they contain the lowest 5% of the negative van der Waals waters. Low van der Waals regions are found in regions with weak polar interactions, and conversely, regions with strong polar interactions have positive van der Waals energy. The balance between Coulombic interactions and van der Waals interactions defines the masked or non-clashing region. Next, let us take a look at the order grids. These are always shown in light blue mesh, and they show the fraction of water entropy lost due to electrostatic interactions. A value of 1.0 means the site is highly ordered, and displacing water from there will liberate almost all this rotational entropy, which is approximately 2.4 kilocalories per mole. A value of 0.0 means the water orientation is completely degenerate, and displacing it will not liberate any rotational entropy. The energy gained by displacing water is primarily entropic. Enthalpy mainly serves as a filter that discriminates between different ligands. And the next type of grid is the mask grid. These are shown in a gray mesh. They are an accurate description of the solvent accessible surface, calculated as regions where the minimum Coulombic interaction plus van der Waals energy is below a certain threshold. Examining the mask grid clarifies where water fits and where it clashes. This displaced region of the apple pocket contains the volume of the apple mask minus that of the complex mask. To speed up ligand calculations during a stabilization run, the ligand analysis is limited to the region within the complex mask by default. Next, let us take a closer look at the binding site. To do this, we are going to use or analyze the neutral difference free energy grid. The neutral difference free energy grid maps the polarity throughout the binding site. And as shown here, the ligand displaces regions with both negative, that is the yellow or gold areas, and positive, that is the purple areas, neutral difference free energies. These energies represent a polarity scale. Negative regions favor polar groups, while positive regions favor non-polar groups. The hydroxyl oxygen nicely substitutes for solvent that acts as a hydrogen bond acceptor. The region in the upper center, on the other hand, contains solvent interacting with a pair of tyrosine hydroxyl that is displaced but not replaced with a similar group. This suggests placing a polar group into this site. Another way to examine the binding interactions is to use the water orientation extension. To use the water orientation extension, select Extensions, Water Orientations. And in the water orientation extension, we are going to select the last grid in the drop-down. And we are going to change the excluded free energy range to minus 0.5 up to 0.5 kilocalories per mole. We're also going to change the minimum order to 5%. And then we'll click Update. And I'm going to close this window so we have a better view of our binding site. If you look at the binding site now, you see there are lots of waters in different orientations. So the water orientation presents a nifty way to display the most probable water orientations for each point in the calculation, and these are filtered to show only the dominant local minima and maxima. It also makes it easy to determine where waters donate or accept hydrogen bonds and where waters do not make any significant interactions. So this information, combined with the displaced in neutral difference-free energy, indicates both the magnitude of the free energies and the geometry that must be taken into account when positioning a substituent on the ligand. We can also examine the protein-ligand complex grid by opening the complex protein item in the list window. So if you scroll up in the list window, there's an item that says complex here, and select the neutral difference-free energy grid, and also update the water orientation. So make sure the complex is selected and the ranges are fine, and click Update. And it is also a good idea to label some of the residues here. So I'm going to go into Style Control, Add Labels, Residue Info, and click OK. And go back to the list window. The display shows two regions, the bottom region and the top region, of negative free energy. The region at the bottom, where solvent interacts with two histidines residues around here, and the amide NH of the ligand, and a smaller region at the top that interacts with tyrosine residues. And if you look at the stabilization neutral difference-free energy by going to stabilization, neutral difference, stabilization free energy, it is clear that only the lower region is stabilizing the bound ligand. That's adding weight to the idea of displacing water in the upper region. This concludes this tutorial on how to analyze SZMAP stabilization results grids. Please feel free to explore the other results grids as well. There is also more information in the SZMAP documentation.